Okay. Welcome to Phobos and Deimos, the moons of Mars. We're very pleased today to have Dr. Robin Canup with us. My name is Ken Ramsley. I am the class moderator for today. This online graduate level course is sponsored by the Solar System Exploration Research Virtual Institute, otherwise known as SERVI. The Institute has a number of teams that are actively engaged in Phobos-Deimos systems exploration research. This particular SERVI class is co-sponsored by the University of Central Florida's Center for Lunar and Asteroid Surface Science, otherwise known as CLASS, and Dan Britt is the principal investigator, and also by Brown University's Evolution and Environment of Exploration Destinations team, otherwise known as SEED. And Carly Peters is the principal investigator here. As in previous weeks, to help facilitate online interactions, we have some ground rules. Because of the size of the audience, online audio is limited to the speaker and moderator. Throughout the class, however, we encourage everyone with a comment or question to type this into the Adobe Connect chat window. Led by the moderator, we'll address these comments and questions during the 30-minute a Q&A session that follows the 1-hour lecture. Lecture readings, key questions, slides, videos, and speaker bios are available on the class website. And the class website you can link to that in the chat box. There's a link there right now as I speak. Last week, Dr. Joe Burns addressed the origin of Phobos and its dynamical evolution. And today's lecture continues this topic by focusing on the conditions and processes that are required to produce these moons in the vicinity of Mars. Our speaker today is Dr. Robin Canup. Dr. Canup received her PhD in Astrophysics, Planetary, and Atmospheric Sciences at the University of Colorado. She joined the Southwest Research Institute in 1998, and as an Associate Vice President, she leads the Institute's Boulder office staff. She's a principal investigator in NASA's Emerging Worlds, Planetary Geology and Geophysics, and laser programs, and is co-investigator of the Institute for the Science of Exploration Targets, known as ICET, which is the Southwest Research Institute-led SERVI program team. Dr. Canup's main research areas are the origins of the planets and satellites. Her recent research projects address the origin and early evolution of the Earth-Moon system in the giant impact scenario, hydrodynamical simulations of large-scale planetary collisions, the formation of gas planet satellite systems, the origin of Pluto-Charon by a giant impact, the formation of Saturn's rings and inner satellites, and the origin of Phobos and Deimos. Today, Dr. Canup will speak on the origin of Phobos, co-accretion, or big impact. Robin?
Thank you. I want to start off by extending a thank you to the organizers of this course. I think it's been a big success. I personally have really enjoyed seeing the other lectures. I think it provides a really unique opportunity to have detailed discussion across disciplines, and so thank you. I'm going to start by reviewing. Anyone who's seen the prior lectures is familiar with these constraints, but I'll review them, the basic properties of the system that are most relevant to models of its origin. Phobos and Deimos are both very dark objects. We've heard through a number of talks, I remember Andy Rivkin's in particular, the challenges of interpreting their relatively featureless spectra, but in general, they resemble some material from the outer asteroid belt region. They're very small compared to Mars. Their combined mass is of order 10 to the minus 8 Mars masses, and that's very small for the largest satellites around a solid planet. Of course, Earth's moon is very large by comparison, containing about 1% of the Earth's mass. But even the small moons of Pluto contain a somewhat larger fractional mass compared to that planet, so they're very small. They're extremely regular satellites. By that I mean they're prograde. They're both orbiting in the same direction as Mars's spin on nearly circular orbits, and they're nearly coplanar as well. And their orbits are quite compact to the entire region over which Mars might have satellites. So for a prograde satellite, it could be stable in orbit around Mars if it orbited within roughly about half of Mars' hill radius. The hill radius of Mars is about 300 Mars radii. So the complete volume of space around Mars that could have satellites, prograde satellites, extends to roughly 150 Mars radii. And if you look at the irregular satellites of the outer planets, for example, they're generally located between about 10% and 50% of their planet's hill radius in terms of their distances. But these satellites are much closer to Mars than that. Now currently, wrong forward button here. Currently, as shown in the bottom picture here, Phobos is of course quite close to Mars. It's tidally evolving inward. It's located about 2.8 Mars radii from the center of Mars. Deimos is currently orbiting at about 7 Mars radii. Now in his talk, Joe Burns gave a very beautiful description of the tidal interaction between the moons and Mars. To briefly review, the so-called synchronous or co-rotation orbit around Mars, that's the orbital distance where the orbital period matches the Martian day, is located about 6 Mars radii. So for any moon outside that distance, the tide that the moon raises on the planet forms somewhat ahead of it, and interaction with that tide leads to a positive torque on the moon's orbit, and the moon's orbit expands. Conversely, for any moon inside that distance, the tide it raises on the planet forms behind it, and it tends to get a negative torque from that tide, and its orbit spirals inward. So Phobos and Deimos are straddling that critical distance. And if we integrate their orbits back to a presumed primordial origin, we see that although they're quite widely separated right now, they likely formed much closer together, straddling this co-rotation distance at about 6 Mars radii. We also see that while Phobos has tidally evolved inward by a lot, Deimos has evolved only a small amount due to its smaller mass and more distant location. So there are 3 general ways to form moons around solid planets. The first is intact capture. I'll just talk a little bit about that to recap what was really the focus of Joe Burns' talk. There's also co-accretion. In terms of solid planets, this is collisional co-accretion, when smaller objects in heliocentric orbit undergo collisions within the Hill sphere of the larger planet and form a debris disk from which satellites can then form. And then there's formation of satellites through giant impacts. This is the mode of origin that's been extensively explored in the context of our moon and Pluto's Charon, of course. In this mode, you have a very large impactor, say with 10% or more of the planet's radius, hit the planet in an oblique impact, and that collision ejects material into a circumplanetary disk from which satellites can then accrete. So I'm going to start by recapping a couple of the points made during Joe Burns' talk. In the simplest mode, intact capture involves a single object in a close flyby past Mars, and if you have some type of energy loss during that flyby, you can potentially transfer a previously unbound orbit into a bound orbit. And one example that Joe talked about and that has been explored in detail for this particular problem is the idea that perhaps early Mars had an extended atmosphere, and that satellites could be captured as they pass through that atmosphere due to the effects of aerodynamic drag on their surfaces. The challenge with this type of model in general is that if you invoke a substantial enough atmosphere to capture Phobos and Deimos during a single flyby, then as they continue to orbit within that atmosphere, the same type of atmospheric drag will cause their orbits to spiral inward. And so in general, if you have enough drag present to capture an object, there's also more than enough drag present in an atmosphere, for example, to lose that object, unless you can invoke a well-timed and perhaps relatively rapid removal of that atmosphere soon after an object is captured. There have been a number of papers in recent years that have explored a variation on intact capture, in which the objects encountering the planet are actually in a binary before they fly by the planet. So in this plot, it's a little hard to see, but on the upper right portions of the plot, as the orbit is incoming into Mars, there's actually two lines there. There's a gray and a black line. So those are showing the orbits of a binary as it approaches the planet. Now, if the separation of the binary, as it undergoes a close pass by the planet, if that separation becomes comparable or greater than the mutual Hill radius of those objects, one of the objects can become unbound during the close pass, and you essentially have an exchange reaction where one member of the binary ends up in a high eccentricity orbit around the planet while the other member continues on in an unbound path. And this is now a leading idea for the origin of Triton. The figure here is from Agnor and Hamilton 2006. And this type of mechanism has been explored for a number of other types of systems as well. In terms of the Phobos-Deimos system, there are two basic challenges in applying this type of model. The first is, at the simplest level, you'd need this event to happen twice to form two moons. And while if you were captured into this very elliptical orbit, like we think Triton was, one can invoke very strong tidal dissipation within the satellite at its periapse distance. You can use that strong energy dissipation to circularize the orbit. You don't have the same freedom to explain how inclination is removed. And so you would expect in general, if you captured objects through this mechanism, they would retain a substantial inclination relative to the equatorial plane of Mars, because these objects would have been encountering Mars with random orientation. And in fact, Triton is on an inclined orbit in the same way. And so it's not clear how even this type of mechanism could produce two objects with both ending up in the equatorial plane. So intact capture as a mechanism is indeed relatively improbable. And by relatively here, I mean that it's typically less probable than a direct collision with the planet, although not always so, or than just a scattering event in which a previously unbound object remains unbound after the close encounter. But there are ways to get capture. What makes intact capture so problematic for Phobos and Deimos is really the nature of that there are two of them, and the nature of their orbits, that they're very circular, and in particular, that they're very low inclination. And we had very interesting discussion and back and forth in the Q&A session after Joe Burns' talk about whether this event would be impossible, and whether claims to impossibility before have been followed by revealing of possibility. And so I just wanted to clarify, dynamicists are not saying in any way that intact capture is an impossible event. There are lots of objects that we think are captured throughout the solar system. And actually in the last 20 years subsequent to Joe's review chapter in the Mars book, there's been a lot of work on how capture can occur. Yet it still appears extremely improbable that intact capture formed these two moons, really because of the nature of their orbits. And that's not to say that one can't come up with scenarios where they could be captured intact, but that to do so requires long strings of unrelated events, each one of which is already a low probability. And the much more straightforward explanation, given the orbits of these objects, is to assume that they formed in situ, that they accreted from a disk, a dissipated disk, around Mars. Now, the origin of this disk can occur from a number of different ways. But to reiterate Joe's point at the end of this talk, and actually during this talk as well, the overall properties of the system most strongly indicate an in situ origin. That's not to say intact capture is impossible, but it appears much less probable. So let me start by talking about collisional co-accretion as a way of producing an equatorial ring or a disk around Mars from which Phobos and Deimos could accrete. So this is a process that's been studied by a number of workers. I list a number of references of just the investigators here in case anyone is interested. And there's lots of papers involving this topic. At its most basic form, collisional co-accretion is when you have a planet and it's embedded in a swarm of much smaller objects. And as two of these objects are passing through the Hill sphere of the planet, they undergo a mutual collision, a so-called free-free collision. And you dissipate enough energy in the collision to transfer unbound orbits to a bound orbit. So initially, the debris from one of these collisions is on a high eccentricity, high inclination orbit. But so long as you have a ring or debris, you're going to have inelastic collisions between the objects in this ring or disk. And those inelastic collisions will damp the relative motions of the particles, which will lead to the circularization of their orbits, and it'll also reduce the mutual inclinations because the collisions will tend to damp out the relative up and down motion of the particles as well. So while you start with a highly eccentric inclined ring, collisions can theoretically then produce an equatorial disk from which you can form the satellites. Now, if you have a very frequent rate of these free collisions within the Hill sphere of Mars, then another mode of collisional co-accretion can become important and in fact dominate. So if the time to deliver mass into orbit around Mars from one of these free collisions becomes comparable to or shorter than the time for the debris from any one collision to accumulate back into a satellite, then you can produce a quasi-steady-state disk around the planet. And if you have a steady-state disk, then it's got a big cross-section. And heliocentric objects can start to collide with the disk objects and be captured into orbit around Mars. And so this mode is known as the bound-free collision mode. And usually, if this becomes important, it starts to dominate because the cross-section of the disk is much bigger than the cross-section for a free collision. So there have been a lot of works that have investigated the fundamentals of this problem. I'm going to walk you through just some very simple estimates for Phobos and Deimos in particular. These are very simplified, but hopefully they will help reveal some of the basic parameters that are important for this process. So let's consider that Mars is embedded in a heliocentric swarm of n objects, each of radius r. So these are all much smaller than Mars. So we're going to calculate the time scale for two of those small particles to collide with each other. And we'd like to know how often that occurs within the orbital stability region of Mars. So say within half of a Mars Hill radius. So the first expression in parentheses in the first equation is just the time scale for a collision anywhere in this annulus around Mars's orbit, the so-called particle-in-a-box collision timescale. So the numerator here is just the volume of this annulus around Mars, 2 pi times Mars' semi-major axis times the width of the annulus around Mars, times its height. And the height of the disk is crudely the dispersion velocity of the particles, that's the velocity due to their eccentricities and inclinations, divided by the orbital frequency. And then in the denominator are the number of these background objects, their size, and their dispersion velocity. So that's the particle-in-a-box timescale. That's the time for one collision to happen anywhere in this annulus. And if we want to know the inverse of the rate of collisions within the heliosphere, we multiply that times the ratio of the volume of this whole annulus compared to the volume of the sphere around Mars of interest. So in going from the first equation to the second equation, I've done a couple things. First, I've defined a surface density, lowercase sigma, of the small objects. So the surface density is the total mass in small objects over the area of the annulus. So I'm replacing the total number of objects, n, in the first equation, over 2 pi a delta a, by sigma divided by the mass of a single object, 4/3 pi r cubed rho. Right? And then that translates the square of the area of the annulus in the numerator over the square of the number into 1 over the surface density squared, and it introduces a mass squared to the top, so we've got an r to the 6th, and we had an r squared in the bottom, so in the end you end up with an r to the 4th dependence after you do this transformation. The second thing I've done is I've replaced the height of the annulus with the velocity dispersion over omega. So if we'd like one of these collisions to be probable in some amount of time, we can see for a given size object what the surface density of the background would need to be to give us that collision timescale. So if we wanted one such collision to form Phobos and Deimos, we'd want the two objects to each be roughly half the combined mass of Phobos and Deimos. So for each of these background objects to be roughly a 10-kilometer size object. So in the last equation here, I'm looking at 10-kilometer size objects. So a single collision capable of delivering the total mass of Phobos and Deimos. And it would require a separate type of model to estimate how long such a background population would persist. But just as a crude estimate here, I've set that time, the desired time, to be 5 million years. And for 10-kilometer objects, each with density roughly of Phobos, you need a background surface density, that third term, to be about 0.1 gram per square centimeter. If you assume a velocity dispersion, v, comparable to the escape velocity of Mars. Okay, so what does that mean? The first thing is that the current populations of small bodies are insufficient to make these collisions probable. So let's consider an extremely crazy extreme situation. Let's take the whole mass of the current asteroid belt, put it all in 10-kilometer objects, and plop it down right on Mars's orbit surrounding Mars. If you did that, you'd expect one collision in 4.5 billion years. And yet, of course, we know that the current collision rate with Mars isn't that high by a lot. So to make an event like this probable, you have to invoke a population of objects that no longer exist. The most likely time for such a population to exist, of course, is the primordial disk when Mars was formed. So if you wanted, again, this collision, one collision to form Phobos and Deimos, you'd need R to be of order 10 kilometers, in which case, if sigma is of order 0.1 in CGS, that's roughly equivalent to 1/10 of Mars's mass surrounding its orbit. So that's a relatively large mass to have all in small objects after Mars is finished accreting. perhaps it's not implausibly large, but it is a substantial population. And so I think it's an open question and an interesting question that should be pursued, whether or not current planet formation models would suggest that such a large population of small objects would be expected. Now, as I mentioned, alternatively, if you make these co-accreting collisions occur frequently enough, you can produce a steady-state disk around Mars. So looking at our equation again, for a given total mass in the background, it's very sensitive, the timescale is very sensitive to the size of the objects. It's that r to the fourth term. So if we considered individual objects in the background that were much smaller than Phobos and Deimos, are much less than 10 kilometers, then you could really shorten the time between these collisions within Mars's hill sphere. And if it got short enough that it was comparable to or shorter than the time for that debris to reaccumulate, which roughly for circumplanetary disk is often, say, 100 years, maybe 1,000 years, then you could be delivering mass and you could create a disk in steady state and then have free objects combined with that disk, and you could increase the delivery rate of material to the disk. Now, in that case, if you had background with much smaller objects, of course, you have a lot more of them. You have many more of these collisions needed to build up a total mass of Phobos and Deimos. But actually, at least based on the models that have been done largely for other situations, including the moon or the regular satellites of the outer planets, it looks like once you get into this mode where you have a steady-state disk, if you invoke conditions necessary to produce that, then generally you'll form more massive satellite systems than Phobos and Deimos. Say with mass, satellite system masses compared to the planet of 10 to the minus 5, 10 to the minus 4. That might not be problematic because in the same way that Phobos is tidally evolved inward and will be lost soon, many larger or more interior satellites could have been lost inward tidal evolution to Mars too. So forming a lot more massive systems to begin with is not necessarily a problem. You know, these are sort of the two basic modes of co-accretion that one could appeal to, depending on the nature of this background population of small material in Mars's vicinity soon after it formed. Now, in either one of these modes, the scale of the disk, in terms of its radius that would form, is a function of the specific angular momentum distribution of the captured material. As Joe described in his talk, when you have objects in a disk undergoing mutual collisions, they tend to damp energy but roughly conserve angular momentum. And so the bottom equation here reflects that initial orbits that were high eccentricity with an initial semi-major axis would tend to collapse to a characteristic, after collisions, to a characteristic semi-major axis. That's a function of those quantities. And this could be tuned to create a compact system with an outer edge near Deimos. But it's not a well-constrained parameter. It's not, in fact, it's for an individual collision, one would have to consider a probability distribution. If you were forming a disk, it's perhaps a little more understood where its outer edge would be. But this is an important element of the problem as well, that at least for this system would need to be looked into. So if we form Phobos and Deimos from collisional co-accretion, what would it say about the nature of these objects? In order to end up with a disk or a ring that will produce a low inclination circular orbit, you need to have taken these objects and basically blasted them apart, right? So that the subsequent collisions between their pieces can collapse things to a disk. If you just look at the relevant relative velocities for these things coming in, there's plenty of energy for these collisions to be disrupted. That is what you would expect. And in fact, if you look at the specific impact energy and just put half of it into heat, there's plenty to both to both melt the rock and to vaporize any volatiles that were present. Now, with regards to the latter, for the co-accretion process in general, these small objects need to be in the same orbital region as Mars. And that's because the mechanism favors very strongly low velocities at infinity objects. If prior works have estimated that if an object had a velocity infinity greater than a few kilometers per second relative to Mars, so this is before any speed up due to Mars's gravity, this is just velocity infinity, then you simply wouldn't have enough dissipation within a characteristic collision to transfer from an unbound orbit to a bound orbit. So this mechanism will work best for material that formed alongside Mars's orbit around the Sun. And because of that, you would expect that probably the incoming material and the material that forms Phobos and Deimos is probably going to be volatile poor. It was within the snow line, within the solar nebula. If you did have some volatiles within the parent objects before the collision, once they get dispersed and those volatiles get released from pressure, the escape velocity from Mars turns out to be comparable to or less than, depending on distance from the planet, of course, the expected thermal velocities for molecular water vapor and certainly for H2 in particular. So you'd expect the moons to be volatile poor. You'd also expect them to not be single intact objects. You would expect rubble pile interiors, and this is because although the initial collision is energetic enough to melt the rock, the cooling time for dispersed debris is much shorter than the time to reassemble Phobos and Deimos. So the debris will be melted, dispersed, then cool, and then the cooled material will accumulate. And as you're building Phobos and Deimos, they're so tiny that the energy of accreting them hardly heats them at all. So once that material cools from this initial collision, you won't expect it to reheat up or remelt as the object forms. So you'd expect rubble pile interiors with substantial bulk porosity, which, broadly speaking, is consistent with what we think these moons look like. Okay, so now let me turn to trying to form these moons from a large impact of Mars. So this mechanism, of course, we've studied for the moon in Charon. I'm going to attempt to run a simulation here of the moon forming event. Let's see if this will work. So this is a three-dimensional SPH simulation of the impact of a Mars-sized object with the Earth, impactors in the upper right, color scaling with temperature here. Blue is molten rock, roughly. Red at low pressure is vaporized silicate. Okay, let's jump ahead a bit. But the characteristic kind of order of events in these type of collisions is that you have an initial off-center impact by an impactor that's large compared to the planet. So there's some fraction of the impactor that's grazing past the planet. The impactor is typically destroyed, either by the initial impact or sometimes part of it by a secondary impact. But a predominant characteristic is that you have this initial collision, part of the impactor material streams out ahead. But the oblique impact, because it's oblique and because the impactor is large compared to the planet, it imparts substantial rotation to the planet in the direction of the impact. Now there's also effectively a shock wave distorting the surface of the planet where the impactors came in. And that shock wave, because of the rotation from the impact, rotates strongly ahead of where this impacting material is. And so in the hours just after an impact, essentially you have this big distribution of material from the impactor that's being stripped apart. And in general, the inner portions of that material are ahead of the outer portions. angularly. So interaction between the impactor material leads to a positive torque on the outer material. In the same way a trailing spiral arm transfers angular momentum outward, this is sort of a trailing structure of impactor debris, and it transfers angular momentum outwards as well. In addition, the outer part of this impactor debris field sees this distorted shape of the Earth that's rotated ahead of it. It's like a giant tidal bulge on the Earth for the few hours after the impact, and it gets a big positive torque from that interaction as well. And it's the combination of those things that basically allow material to get its periapse lifted substantially above the surface of the planet. Vaporization, pressure gradients associated with vaporization can also do that, and in different types of impacts, those can be more important compared to gravitational torques, but gravitational torques are usually, for most impacts, particularly low velocity ones, the dominant mechanism. So on the next slide, I'm going to show you the animation of the same type of impact. It's the same impact, where I'm going to run it backwards in time. So the final image here is the disk, the final frame from the prior animation. And here the color scheme is corresponding to the fate of the material. So yellow particles are those particles that ended up in the disk, blue particles are those that ended up in the planet, and the few red particles, which are hard to see in this frame, are those that escape the system entirely. And so I'm going to play this back, and it'll loop, but you can see as you go backwards in the animation where the yellow particles, where the stuff in the disk comes from. And it's from this outer region, predominantly, it's from this outer region of impactor material. Now again, as you change the parameters of the impact event, the specific proportion of material that comes from the planet, the target, versus from the impactor changes. But for large impacts, it's never completely from the planet. It's sometimes almost completely from the impactor. And there's a lot of impacts where it goes. So when the impact origin was originally proposed for the origin of the moon, one of the concerns was that one might have to very finely tune the properties of the impact in order to get any material into bound orbit around the planet at all. Because if you consider a ballistic orbit, if you shoot a bullet from the surface of a spherical Earth, the bullet does not go into orbit around the Earth. It either re-impacts the Earth or escapes. And so there was initially concern that it might only be a very narrow range of impacts that could really get around through non-ballistic interactions would produce a disk. But many hundreds of these simulations have been done with different methods by many different groups over decades now. And actually what we found is that, by and large, most of the impacts that are accretionary, that is, that are low enough velocity to add net mass to the planet, most of those also eject some fraction of material into a circumplanetary disk. And that actually the outcome of producing a disk appears a very general. So this plot shows results from lots of different SPH simulations of impacts. Here the color is corresponding to the ratio of the impactor mass to the total colliding mass. So the red points are an impactor that contains 45% of the total mass, so almost an identical, equal size collision. Whereas the black points are impactors that contain roughly 3% of the target's mass, much smaller. On the y-axis, I'm plotting the estimated moon mass compared to the planet mass, and that's just a very simple analytic description that's a function of the disk mass and the disk angular momentum. As a function on the x-axis of the scaled impact parameter, so 1's a grazing impact, 0 is a head-on impact. So a couple basic trends emerge from these, and these have been seen pretty consistently now. And that is, as you increase the relative size of the impactor compared to the target, as you go from black to red, you produce proportionally more massive disk. You have a larger mass of the impactor that's grazing past the target that can be effectively torqued into orbit. And for a given impactor mass, as you make the impact more grazing for a low velocity, you also increase the disk mass as you move left to right on this plot for a given color. And that's because as you make the impact more oblique, more and more of the impactor mass is in a good place to be torqued into a bound orbit. Now, in terms of impact velocities, the biggest disk masses are usually produced for an impact velocity near the escape velocity of the system, of the colliding objects. And for every impactor mass and impactor angle, there's usually a maximum impact velocity relative to the escape velocity. When you get above that, most of the impactor and most of the impact angular momentum tend to escape rather than form a disk. So usually, for all other things being equal, as you increase the impact velocity above the escape velocity by tens of %, you may increase or maintain the disk mass. But then if you get impact velocities that are too high, the disk mass that you produce will rapidly decrease, will rapidly fall off as you increase impact velocity further. So the idea that the satellites could have been formed by an impact with Mars was advocated years ago, in particular by Bob Craddock. We know from all of these simulations of impacts that the collisions that produce extremely low mass disks compared to the planet. So if one were to imagine a disk that initially had a similar mass to the current Phobos and Deimos mass, or maybe within an order of magnitude, say, that those types of impacts produce very compact disks that are very close to the planet, have low specific angular momentum. They don't produce debris that's really far away, like where Deimos is right now. This is a plot from a paper by Rosenblatt and Charnot in 2012, and they studied the evolution of such a compact disk and how it might spawn satellites with time. So in the upper left, they've combined a model for the evolution of a continuous disk interior to the Roche limit at Mars, with a model for the accretion and accumulation and evolution of small satellites outside the Roche limit. So they start with the disk inside Roche limit. Then they have a prescription for how the disk will spread radially due to collisions within the disk. As material spreads onto the planet, it's removed from the disk, but as material spreads outside the Roche limit, it can accrete into these little satellites. And the satellites can merge with each other. And as the satellites interact resonantly with the disk interior to them, they migrate outward. They get a positive torque from disk interactions. In the same way that the little satellites just outside Saturn's rings, when they resonantly interact with Saturn's rings, they get a positive torque and their orbits migrate outward. The general result is you can spawn lots of appropriately sized objects from a compact disk, and initially they migrate outward due to resonant interactions with the disk. But so long as these objects stay interior to that synchronous orbit, which is at 6 Mars radii, and all of the satellites formed from the Roche interior disk in their simulations did, then eventually the disk mass decreases enough, and the disk torques weaken enough, that tides take over and they pull the satellites back in. So for example, in this one simulation, you form lots of moons, but eventually the moons all tidally evolve inward and are lost. So what's the way around this? I'd argue that you have to look towards a different scale of impact than one that would produce just Phobos and Deimos to get an impact origin mechanism to work naturally, or most naturally as you can. So you need to consider a big impact with Mars. Now we know from the isotopic limits on when Mars's core formation was complete that Mars probably finished forming a lot earlier than the Earth did. Say a million or a couple million years versus maybe 50 million years for the Earth. Now based on that, you would think that Mars did not undergo the same protracted period of giant impacts that the Earth did. However, if you just look at the rotation rate of Mars, which is 25 hours, and you ask what kind of impact do you need to just explain that, then it's been known for decades that that tends to implicate at least one impact by an object with few percent of Mars's mass. Now, we'd need an impact, obviously, to form a disk with at least the mass of Phobos and Deimos, but that's just a lower limit, because we could have had a much more massive satellite system in the past, and a lot of the inner satellites could have been lost if you had inner satellites to inward tidal evolution. Now, a big impact has the advantage that it can form a more radially extended disk. So it can get you around this problem that I showed in the previous plot from Rosenblatt and Charnow, where if you start with a compact disk, you spawn moons, but you lose them all. If you start with a big impact, you can have a broad disk. But you wouldn't want the disk to be too broad, because if the disk edge extended way beyond Deimos' orbit, you should have formed satellites outside Deimos. They would have tidally evolved outward, and you'd expect to still see them today, and we don't. So for an impact origin to work, you'd actually, I would argue, need to say that the outer disk edge was near where Phobos Deimos started out, say 5 to 8 Mars radii. So here's an example simulation from some work Julian Semmel and I did a year ago. So this is the impact of an object containing 3% of Mars's mass with Mars. Very scaled down version of a moon-forming impact. It produces a much smaller disk, of course, than a moon-forming disk. The disk here has 7 times 10 to the minus 4 Mars masses. This is still, of course, orders of magnitude more mass than in Phobos and Deimos. But this is the type of collision, a type of collision, that gives you a planet rotating with approximately the current Martian day. So we did an initial series of 10 of these simulations, and these points are results from those 10 impact simulations. So I'm plotting the maximum equivalent circular orbit of this debris in Mars radii, effectively the outer edge of the impact-generated disk produced by each of these impacts as a function of the planet's rotational day after the impact. And for these initial 10 simulations, we made the simplifying assumption that Mars was not rotating before the collision. But what emerges from that simple study is that impacts that give you Mars's day, that are near that vertical dashed line, appear associated with disk whose outer edge is near what we think the initial formation distance of Phobos and Deimos was. And that's a very compelling result. It didn't have to be that way. I mean, if you did a plot like this of typical moon-forming impacts, then yes, most of the mass of moon-forming disk is located close to the planet, but there's a small amount of the mass that goes way out, maybe with an outer edge of 15 or 20 Earth radii. And so it didn't have to be the case that impacts capable of producing the Martian day would give you a disk edge at the right place, but at least based on this very limited and still not high enough resolution set of simulations, it looks promising. But the main issue, the big elephant in the room, is that an impact would produce a disk that's orders of magnitude more massive than Phobos and Deimos. So how can you really get rid of all that mass and then just have Phobos and Deimos remain? And we don't have an answer to that yet, but this is a schematic of an idea for how that might go. So initially, as represented by the top frame, you have some disk that extends out to roughly Deimos' accretional zone. And the outer parts of that disk accrete into Phobos and Deimos. Now the disk is much more massive, and so in the inner parts of the disk, near and somewhat exterior to the Roche limit, you'd form massive moons, 100-kilometer scale moons. But if those moons, as you saw in the Rosenblatt-Charnow scenario, if those massive moons moved out some due to disk interactions, but then moved in some due to tidal evolution, and they never crossed co-accretion, you might be able to lose nearly all of the mass initially in this disk to inward tidal evolution. And if you could preserve a couple little moons formed at the outer edge of this disk, maybe you could produce a Phobos and Deimos analog system. This is a challenging thing to actually demonstrate. You need much higher resolution than we've used here. This model didn't include tides either, but that's a a crude schematic for how you might be able to get a successful case. So we did 10 simulations of Mars impacts, and then this year, Citron et al. Published a paper on the same topic. They published another 10 impact simulations. So everything I've said so far is really based on 20, which is a small number, relatively low resolution impact simulations. Lots of things that will ultimately be important haven't been included yet, like pre-impact rotation in Mars, and the accretion model doesn't have the right resolution yet. But so far, at least, there's nothing that stands out as saying that this couldn't work in terms of an impact origin. And actually, the result that the disk produced by the type of impact, the first one you try to explain Mars's rotation, gives you the right radial scale of a disk, I would say that's a very encouraging result to me. And again, the takeaway is that Mars did have a much more massive satellite system, but you just lost these inner moons to inward decay onto the planet early on. Now, I should mention, I pointed to Mars's rotation as evidence of a big impact, but there's another separate constraint, and that is the Borealis Basin. If you look at the types of impacts that could give you Borealis, in terms of impactor mass, impactor speed, impactor angle, and you look at the types of impacts that can give you the Mars day, there's substantial overlap of those two phase spaces. And this was emphasized in the Citron et al. 2015 paper. And so, at this point, it appears possible that you could actually have one impact that leaves Mars with the right day, produces Borealis, and Phobos and Deimos too. Now, you might not have to do that. You might, if you think the hemispherical dichotomy is a non-impact origin, you could form Phobos and Deimos by the impact that left Mars with its current day. There is a regime of Borealis-forming impacts that probably might not be so good at producing disks, but could still produce the basin. But the point is that you could do a couple different things. You could satisfy a number of different constraints with one event potentially, which is also, I think, intriguing. So if they were formed by impact, again, what does this mean for the moons? Their composition relative to the composition of Mars versus this impactor. Now keep in mind, an impactor with 3% of Mars's mass, this is still a big object. This is a 1,000-kilometer radius object, 50 times the mass of Vesta. So that's the impacting object in this kind of scenario. So the moon's composition, where it gets its material from, will be a function of what fraction of the disk, and what fraction of the outer disk in particular, I would argue, comes from the impactor versus the planet. And, we're not in a position to be able to say what that fraction is based on this very limited number of simulations so far. Now, in theory, because you don't really need to produce that massive of a disk, perhaps, to get this picture to work, it's possible that you might be able to have a relatively large impactor velocity in infinity and still produce a disk sufficient for making Phobos and Deimos. We haven't done this. We haven't simulated this regime yet. But if you could actually have high impacts at velocity, what this means is the impactor could potentially have originated in a more distant orbit than, say, the small objects that might contribute during a co-accretion scenario. For the same arguments I described for the co-accretion model, you'd again expect them to be rubble piles in the giant impact model. And you'd expect them to be volatile poor. Even at Deimos's distance, the thermal velocity for molecular vapor, even if it doesn't dissociate, water vapor, is comparable to the escape velocity for Mars. And so, in the simplest rendition, you'd expect these to end up isopolar. So this is my last slide. So I thought it was really interesting when Joe told the story about when he got his reviews back on his Mars chapter, and Stan Peel, and he was Tony Dobrovolsky, I can't remember who reviewer number 2 was, said, "Oh wow, you've given a really fair shot to capture intact capture, even though it's completely impossible." And then he got a review from a spectroscopist, I think Dan Britt, but I may be mistaken on that. And he said, well, you know, this can't explain the spectroscopy. Because it reminded me, the first time I presented this, the reaction was, well, that was really interesting, except we know these objects are intact captured objects. So I'm going to make a plea. This will echo some of the things that Joe said during his talk. It's not that we can't come up with lots of ways to capture objects. We can. People have looked at capture. The problem is the likelihood of connecting an intact capture or intact capture origin with a system that looks like this, extremely difficult. And in situ models just look a lot more promising, and I think they're deserving of more attention and scrutiny at this point. It's possible they'll prove to be incredibly constraining too, and then we'll relook at improbable capture events. Or, you know, maybe there will be some solutions that aren't as unlikely as we might fear, even in terms of their ability to explain the compositional constraints. Co-accretion is plausible, it looks like, if you can make a case for a large population of small objects, primordial such propagation. An impact origin is appealing, I would say, because we know, based on independent constraints, that Mars did undergo these types of impacts. Now, whether that can really give us the Phobos-Deimos system has yet to be determined. Those types of models really haven't been developed yet. And then I'd argue the key questions at this point that I'd love to see folks focus on is, you know, what would be the ways to explain the spectral characteristics from an in-situ origin? And you know, how creative does one have to be to get that to work? And secondly, in terms of a key constraint going forward, to me the volatile content of these moons is all important. Do they contain substantial volatiles, or are they fundamentally ice poor? And here I don't mean a thin outer layer of something that could be delivered by later impacts, perhaps, but rather, is the bulk composition of these objects dry or very ice-rich? Because, as you've heard, the in-situ models generally are most consistent with a dry composition. And so, if they were shown to be bulk ice-rich, that would be a very constraining and interesting piece of data. Thanks.
I'm still on. Okay, can people hear me?
Yeah, I can hear you now. Everything went quiet for a little bit, but now you're back.
Okay. Thanks, Robin, very much. We're having audio concerns here, and we have multiple PCs trying to keep the show on the road. We have a number of interesting questions in the chat box, and I will. We'll go through these. If you can probably see them yourself, Robin, so you can kind of follow along as well. Wesley Chambers starts the discussion by asking, given their orbits, Phobos and Deimos most likely seem to have formed in a debris disk, regardless of disk orientation. Is this a fair statement?
Yeah, I think so. I mean, in terms of the most likely origin, given those properties, yes.
Let's see, Douglas Schwab, roughly what number of additional, I guess he uses the expression now lost moons, moons that have been lost during this process, would be suggested by the model? I mean, we have 2 now, but how many did we lose in the process?
So I don't know. I don't know the answer to that question for the disk co-accretion model. For the giant impact model, it depends on the mass of the disk, because essentially that sets the mass of the inner satellites and their accretion, the width of their accretional zone, and therefore the number of them just outside the Roche limit. But it could be anywhere from 1 to several for disk masses comparable to those that were produced by these simulations I showed.
Okay. Let's see. Justin asks about the gravitational effects of larger moons, I guess moons that aren't there anymore, to throw around Phobos and Deimos during this process, and whether or not these gravitational interactions, well, he says, to have enough to boost the small satellites into co-rotation with the smaller disk. But I would suspect a larger question would be, what would be the gravitational interaction of the moons during this process, and would that have a major effect on the process?
So this is one of the key questions that has to be addressed with accretion models. Hasn't been done so far. So your intuition is very good. If one imagines a scenario where these interactions with the disk inside the Roche limit are very strong, which would drive a large intersatellite outward, and they're very strong compared to tides, the effective tides with Mars, then you can imagine a scenario where these big inner moons evolve out almost all the way to co-rotation, and they would just sweep up any little Phobos and Deimos debris that was nearby before they turned around and came back in due to tides. And so that would be an unsuccessful scenario. You wouldn't leave anything. So I think that's definitely a possible outcome. Not a good outcome for the model, but it's definitely possible. But within the realm of disk masses and tidal parameters, which of course are both uncertain, there's an intermediate range where the inner large satellites move out somewhat due to disk torques, but just like the Rosenblatt and Charnot simulations, they turn around and come back in. And those would tend to be the ones most likely, we think, to leave Phobos and Deimos in their orbits. Now, an issue that I didn't bring up in the talk, but is sort of a next level of question that ultimately has to be answered, is if you make Phobos and Deimos as close together as they could be initially. So you bring Phobos all the way so it's just interior to synchronous and bring back Deimos. They're still separated by quite a bit in terms of their mutual Hill radii. That's maybe, memory serves, 70 mutual Hill radii, something like that. So usually if you had a uniform disk, you tend to form objects that are separated by more like 10 Hill radii. So you may actually need to invoke a little bit of jostling of this outer disk material by some large inner objects to get these objects to have that kind of initial separation. That's pure speculation. This has never been shown in a simulation. But these are the types of issues that have to be addressed by high-resolution accretion models in order to see if this whole picture would hold together. And then, there was another part of that question. So could the interaction of a big moon push a smaller one out? So if you start with a disk whose outer edge is, say, at 5 or 6 Mars radii, could you form a big one inside the Roche limit, have it expand outward, have it catch that guy into resonance, and have him nudge him just outside co-rotation? Sure. So, I mean, I think if you start with a disk whose outer edge is somewhere between 5 and maybe 8 Mars radii, you might find solutions across that range. I don't think it has to be exactly at 7, because you could transport something little out. With that said, I don't think you can start with a disk entirely within the Roche limit, because in that case, the first moon to form is the most massive one. And you can move that out later by having it evolve outward, having a less massive one spawn, capture this one in resonance, and then push it out, but you end up out with a big outer moon. So I don't know if that'll work.
Okay. let's see. The next question is from Emerson, and there's the idea of thinking about the impact on Mars, and I mean the larger question is, you know, how big of an impact on Mars are we talking about? In Emerson's question, he's wondering if the resurfacing of that impact would hide any evidence of the impact, if it were really that large, you know, like a global scale kind of impact. You know, have you given thought as to the nature of the impact on Mars and what we would expect to see on Mars to produce an accretion disk?
Well, I think in terms of the models of forming the Borealis Basin, the giant impact, one of their key constraints is that the distribution of post-impact melt and heating is such so as to preserve the evidence of the basin that we see today. So that's a constraint for those type of models. For the accretion models, I mean, for the production of a disk models, you don't have that constraint, and one could imagine that you could invoke an impact whose effect on Mars would be erased, and that you wouldn't see. Does that answer the question?
Okay. I mean, it's you know, it's sort of a bigger question that isn't related specifically to what happens in orbit, but it does ask the question of, you know, what could we find evidence looking at Mars, I suppose. Okay, Ryan asks, is there a way that we could differentiate impacts from the lost moons on the surface of Mars? Would they look like just any other impact, or is there some way, you know, assuming that we're losing these moons to the surface of Mars, is there a way that we could observe these on Mars, maybe a higher size frequency distribution along the equator or something like that? Has anybody looked into that?
So this has been hypothesized before. Pete Schultz and colleagues and Bob Craddock talked about this in his 2011 paper as well. What you would have is predominantly equatorial debris coming in extremely low velocity grazing impacts. But this material is going to be spiraling inward due to tides. And you won't have a 100-kilometer moon that formed outside the Roche limit, or 200 kilometers even, hit the surface of the planet. It's going to spiral in, it's going to go within its Roche limit, it's going to get disrupted. And how big are those fragments going to be? Well, that's going to be a function of what you think the internal strength was of that big moon, not of little Phobos and Deimos, but that big moon. You would have a population of those fragments, whatever that size would be, depending on the strength, raining down onto Mars's surface, and they'd be coming in very obliquely on very low velocity orbits. So would you absorb those? I don't know. You have a couple variables. The size of those objects. Are they interacting with the atmosphere of Mars as they're coming in this very grazing impact? Did they break up? Did they even form craters? Where was the equatorial plane of Mars at the time? Because while the satellites track the equatorial plane of the planet, while that plane will track that, there is polar wander on Mars, and so it may not be associated with the physical landforms near the equatorial plane today. There have been claims that there is an increase in the distribution of elliptical from presumably high oblique impacts on Mars that one sees, and when you connect these, you can make a potential primordial equatorial circle, so it might be evidence of these impacts. It could be that Mars is heated so much from these impacts that the re-impact does not leave any signature that's observable until today. I think that's all another piece of this puzzle that really deserves some thought, that hasn't received it so far, and that merits some additional modeling. My guess is that I don't know that I could make a prediction based on the models that exist right now to say that.
Okay. Angela asked about let's see, we're getting a little bit of echo here. Angela asks about volatiles that perhaps wind up in the bulk mass of Phobos and Deimos, and I'm wondering if your model accounts for the distribution of the sorts of material that are accreting and being distributed.
Well, what one could obtain from very high-resolution impact simulations would be not only the origin of the material in the outer disk in terms of whether it came from the impactor or the target, but you could actually get an estimate, a crude one, at the limit being the resolution of the simulations. You could get an estimate of the depth in the impactor and or Mars that the material came from that ends up in the outer disk. That's probably about all you can get from the SPH simulations. So then one would have to combine that with a compositional model for an impactor, say, based on the range of velocities at infinity derived from impact models that seem to work, and compare that with the other two pieces of output from the simulations I described to see if you can put together some kind of predictive model for what that material should look like. Well, did I miss it? Let me see. How would you propose determining if volatiles are present throughout the bulk mass of Venus? Well, this, of course, is really challenging. I mean, maybe you can get, maybe you can say something through surface composition based on like classes of objects and meteorite classes. Maybe there are ways through, say, better observations of tidal response to get a better parameter. I mean, right now we have a density, and in that density is an unknown porosity and an unknown proportion of ice. You know, we got there are two free dials you can tune to get a given density. But maybe if the porosity was better constrained by higher fidelity measurement of tidal response, you could bracket ice content to a better degree than we can now.
Let's see, Bill Botke has a follow-up comment about looking for evidence of lost moons on the surface of Mars. Evidently, he back in 2000 looked at this, and also he cites an interesting, intriguing paper by Schultz and others in 1982, and suggests that so far he hasn't found really much of any evidence about that. So I just wanted to point that out. Andrew asks about big inner moons being driven out by the disk torques, let's see, pushing the smaller moons out into a resonant chain. I guess it's sort of the more general question is what kind of processes might be going on, besides just accretion and so forth. These. I don't know. I'm not sure exactly what Andrew is getting at, but just, you can imagine just the idea that.
Yeah, and to be honest, it's the whole interplay of the outward expansion due to disk torques versus the inward motion due to tides that makes this interesting. That makes this not just a very simple standard accretion problem. Okay, so it's the whole interplay of those effects that really makes this problem intriguing to figure out. So if you had inner moons, yes, as inner moons migrate outward due to disk torques, they could very well trap outer smaller moons in mean motion resonance and drive them out too. And that's what I meant when I said, well, if you had a disk outer edge that was at 5, that might work too, because maybe you form a Phobos and Deimos around 5, and then you have an inner object push them out. Maybe. We do know there's a limit to that, of course. We tried to play this game with forming the small moons of Pluto by forming Charon intact and having a debris disk outside of Charon, and then as Charon tidally evolves outward, trap the outer moons, which do appear in resonant or nearly resonant configurations, to then drive those little moons outward. And the trick there is, in at least the overwhelmingly probable mean motion resonances, as you push something out, you drive up its eccentricity. So this is, Neptune, we know Pluto has moved out because of its orbital eccentricity. Well, that's because Neptune pushed it out just a little bit in one of these mean motion resonances. So when you start trying to play the game of pushing out little moons by a lot, you will naturally tend to drive up their eccentricities to probably crossing, and maybe crossing even with the inner large moon's orbit. So there may be some solutions there. There may be some additional challenges there by that process, but it could certainly be important.
Okay, Stephanie asks, looking at the sample return. Okay. I'm waiting for the echo to settle here. Stephanie asks about the notion of what we might find in a sample return. Now, and I suppose that if you imagine the different scenarios of how these moons might be produced, whether or not there's some evidence that could be found in a sample to tell us whether or not it's maybe a co-accretion with Mars, or an impact on Mars, or anything along those lines.
In terms of the kind of broad stroke distinctions, I think the giant impact scenario gives, at least at face, would tend to imply that the material that formed these moons was initially in much larger objects. Now, it does get dispersed. It probably would lose its volatiles if it had any. It would tend to degas. But nonetheless, you might see a composition that you wouldn't necessarily expect from material that had only resided in 10-kilometer or smaller objects, because it's been derived from these much larger objects, perhaps from their crust or even from their mantle. That's one possibility. I do think that you would expect. I've talked about the rubble pile. If you found strong evidence that one of these was really an intact piece, which based on current evidence doesn't look reasonable, but if you had an intact piece, I think that would be a pretty strong argument against the accretion models. Those arguments, those constraints are just as important, if not more interesting, of course. We've talked about the ice content. What's really interesting to me is anything having to do with the depth in these objects that's represented by the spectra that we have. Are these, is this composition possibly an added composition? Have the moons exchanged material? Does composition with depth vary once you get below a very thin outer depository layer? Just some ideas. Not all of those are good. I'm a theoretician.
Okay, well, you see the chat box, we have finished the list of questions, but I have my own question, which is, we teach and study the notion of comparative planetology. We look at different scenarios, and I'm just wondering, as you came to this question of Phobos and Deimos and Mars, what your previous work helped you in insight, or just comparing this system to other systems, how that might help understand this particular process.
Well, to be honest, when I first started thinking about this, which was just a couple years ago, I assumed that these were intact captured objects, and I had really not given much thought to their having been formed by an impact. And it was really only as I read through past works, including Joe Burns's chapter, and tried to start working through scenarios, that I became convinced that intact capture was extraordinarily difficult. And then when I looked at the impact simulations that have been done for other object simulations, it's pretty straightforward to apply those to any planet so long as you're big enough to be in the gravity regime. So it was very directly related to trying to form the outer satellites of Pluto, share on forming impact. We initially used scaling relationships that were based on moon forming impacts to try to infer what the mass that this disk would be, and those turned out to be pretty close to what the simulations produced. And obviously, I mean, it's the same physics as going into studying accretion in these disks that have been used by Krita and Charnot and collaborators to study the accretion of small moons around Saturn and interaction with Saturn's rings, and those that Julian Samaz developed for the evolution of protolunar disk into moonlets. So very, very similar physics, but obviously very different final outcomes, and perhaps due almost entirely to the fact that Mars just has a slow rotational day, which puts this critical distance of synchronous orbit at Mars at 6, versus after a moon-forming impact, the Earth is rotating with a 5-hour or less day. So this synchronous orbit is in its 2 or 2.5 Earth radii. So every moonlet that you form from the Earth will survive. They may merge, but they're generally going to survive. Whereas at Mars, we're going to lose a lot, just as the Rosenblatt and Charnot simulations show.
Cool. Thank you very much, Robin. As we close our session, first I want to thank Dr. Canup for an excellent and informative presentation. Thanks also to those of you in the audience who raised thought-provoking questions and comments. Audience participation is always valuable and appreciated. We would also like to thank our colleagues at MIT and here at Brown from SEED and the class team at UCF for all of their efforts, and Survey Central for a major effort in supporting this online class. Our special thanks go out to Yvonne Pendleton, Survey Director, and to Ricky Guest for technical support that includes Adobe Connect system and behind-the-scenes work that makes what you see and hear actually happen. Next week, we'll be hearing from Dan Shears, who will be speaking on the microgravity within the Mars gravity well. Dan Britt will be the moderator for that class. Thank you all for joining us.